Good afternoon. Good afternoon and welcome to the February 2025 edition of Science Sundays. Here in Ohio, it's almost the first day of the first fall spring that starts tomorrow. If you're new to Ohio, we'll have about 4 or 5 more of them. Today, we have a special guest I'm going to tell you more about in just a minute, but I want to begin with something I said last time, is that science begins with curiosity. That's the thing that brought you here, and it's the thing that drives researchers like our speaker today and our speakers on other occasions to do their work. So we begin together with curiosity. And what happens next is, that we go off to our offices and labs or have to hang out in shabby locations around the world and do all of the research. And we do it with huge teams of physicists and astronomers and all kinds of other scientists from all around the world. And then we come back together to share the results of what we've learned. Because as I said before, science unshared is like science undiscovered. If you know something amazing and you don't tell anybody, it's like nobody ever knew. So we can make things better for everybody by sharing the results. So I want to thank everybody for their enduring interest in this series and for coming today. I see a lot of familiar and happy faces, and that's great. So our speaker today is Professor Paul Martini. He's a professor in the Department of Astronomy. He also has a joint appointment in physics, and he's also a member of our Center for Cosmology and Astroparticle Physics. Oh yeah, I forgot to say, I'm John Beacom. I'm from Physics, Astronomy, and Center for Cosmology and Astroparticle Physics. That's how I know him. So Paul has been at Ohio State since 2005. And he played a really important role in many projects, but especially one that'll be a highlight of today's talk, the Dark Energy Spectroscopic Instrument. It's a massively complex, massively expensive, and massively powerful survey. And Paul played a really leading role in making the whole thing happen. I don't know, he's probably too modest to tell you that directly, so I want to make sure I tell you that now. He was the instrument scientist during the 5 critical years of building and making the thing turn on. So without further ado, let's welcome Professor Paul Martini.
Thank you, John, for that kind introduction. And thanks to all of you for coming today to give me the opportunity to share with you some of the research that I've been doing into the mystery of cosmic acceleration. My goal in this talk is to start off by telling you a little bit about how I got excited by the question of cosmic acceleration, the mystery of cosmic acceleration as I express it on this title slide. And it really is a mystery story. And I'm going to tell you a little bit about how it got me excited. And I'll tell you also a little bit about the background to put the mystery of this question in context. And I'll conclude with some of the recent results from the Dark Energy Spectroscopic Instrument, a project that I worked on along with hundreds of other people. We built a great new instrument that is located at the Mayall Telescope, which is this large telescope here at the Kitt Peak National Observatory near Tucson, Arizona. So I'll start off with a little bit about how I got excited about astronomy and physics. And I started off by being just really curious as a child. I had lots of questions. I always wanted answers to questions like, why is the sky blue? Why can I see the moon during the day? Why does the Earth go around the sun? Why is it cold in the winter? And I also got excited about images of space. I remember when I was pretty young, the Voyager 2 mission sent back these beautiful images of the planets in the outer solar system. And I got really excited about them, trying to understand questions like, why is this one so blue? Why are there such amazing structures on these planets? Why does Saturn have these enormous rings? This kinds of questions also inspired me to look outside of our solar system and look at gorgeous pictures of galaxies. This is one of my favorites, the Whirlpool Galaxy, known to astronomers by the less cool name of M51. The Whirlpool Galaxy is gorgeous. It obviously looks like a whirlpool. It's a spiral galaxy like our own Milky Way. It's about 30 million light years from the Earth. That means that it takes light from this galaxy 30 million years to reach us. So when we take images of it today, we are looking at the galaxy as it appeared 30 million years ago. And that's going to be one of the themes in my presentation, is that when we look at the light from distant objects, beautiful objects like this, other objects that are way, way, way farther away, we are looking at them as they appeared long ago. And in fact, we can use that as a time machine to look at the universe as it was in the very distant past. This galaxy, in addition to being beautiful, also tells us a lot about just what galaxies are like, the common properties of galaxies. We see that they have lots of stars in them. This galaxy has trillions of stars in it. Many of them are newly forming stars, and they give us this bright blue features along its spiral arms. We also see that there's interstellar dust in this galaxy, like there is in the Milky Way, and so on. We learn lots of really interesting things. And when I was a kid, I was just super excited about trying to understand space. Things like, where does the universe come from? What is the fate of the universe? And one of the really formative experiences that I remember from when I was in high school was reading this book, A Brief History of Time, by Stephen Hawking. And this introduced me to two things. One was the wonder of the universe, just how amazing some of the phenomena were in interstellar space, intergalactic space, concepts like black holes, concepts like the Big Bang, this explosion about 14 billion years ago that produced our entire universe. But I think what it also showed me was that it showed me that if I learned more physics, if I learned mathematics, these were the tools that scientists like Stephen Hawking and many others used to try to solve, to try to answer the kinds of questions that I was interested in. And this got me excited about going on and studying physics in college, continuing to also take courses in astronomy. And it also made me realize, and you've probably also realized it by this point, I was very much turning into a geek. I really liked spending my time thinking about these really cool questions. But that's okay. One of the things that I learned about in my physics classes was this concept of the four fundamental forces of nature. These are the strong and weak nuclear force, electromagnetism, and gravity. These are all fundamental in that these forces, combined with our understanding or the language of physics and mathematics, could in principle, even should in principle, in my mind when I was in high school and college, give us an understanding of basically anything. If we had enough data, we could map out how things worked using these tools, these pieces of these raw materials, these construction equipment, this equipment, and our knowledge of physics and mathematics. The strong nuclear force is fundamental because this is how all atoms heavier than hydrogen exist, including calcium, oxygen, everything that is really critical for life, for everything that's pretty, almost everything that's pretty about galaxies like the Whirlpool galaxy. The strong nuclear force is what allows positively charged protons to be crammed next to each other inside of atoms, even though their similar charges would otherwise push them apart by electromagnetic forces. There's also the weak nuclear force that can turn, for example, neutrons into protons, electrons, and neutrinos. It is important for radioactivity, for nuclear power, for medical imaging. There's electromagnetism, which of course is fundamental to things that are in all of our everyday lives, like consumer electronics, even the operation of the projector, as well as the computer that I use to create these slides. And last but not least, gravity, which is the reason why we're all comfortably, well, most of us are comfortably sitting in chairs, and I'm not floating in space trying to talk to you at the same time. But it's also the reason why the Earth formed, why the Sun formed, why the Earth stays at a relatively constant distance from the Sun as it orbits. So exciting, when I was learning about these forces and learning about physics, I got excited that I could use these tools to basically answer any questions that were thrown my way, provided I had enough data and I knew enough physics and mathematics. As you're going to see, I was pretty naive. But nevertheless, I have gotten to do a lot of really amazing things and look at some just gorgeous images of the night sky. So one of the great things about being an astronomer is that we just get to look at lots and lots of pretty pictures. One of my favorites is this one. This is a very small region of the sky. It's 1/10 the size of the full moon that I'm showing here, but it's absolutely filled with galaxies. This is something that's called the Hubble Ultra Deep Field. It's an observation that was taken with the Hubble Space Telescope a little bit over a decade ago. And it's got some just absolutely gorgeous galaxies in it. We see red galaxies and blue galaxies, big galaxies, small galaxies. It's a little bit, sounds like a Dr. Seuss book in the making. And just like in Dr. Seuss, some of these are old, some of these are new. The nearby galaxies are closer, or the larger galaxies are generally closer to us. So we're looking at them at a time when the universe was older, but we're looking at them in the more recent history of the universe. Whereas the most distant objects in this image, these tiny little specks, those are also galaxies. And some of them are so far away that the light from them has been traveling for most of the lifetime of the universe to get to us. Over 10 billion years. To put that a little bit into context, the light from some of these objects, the photons that they emitted and are traveling towards us, that we've only just now detected, those photons were already over halfway here when our solar system formed, about 4.5 billion years ago. So this is really looking back through most of cosmic history. One of the things that is difficult to tell from an image like this is that it's pretty hard to tell exactly what galaxies are at what distances. And so one of the things that I'm going to make as a theme of this presentation is just how we determine the distances to these galaxies. Another thing that you might look at this image and not know are that all of these galaxies are moving away from us. All of them. And I'm going to tell you how we know that and why that is the case. But first, I'll talk about the distances. The way we determine distances to galaxies is quite a bit different than the way we determine distances in everyday life. We can't use a tape measure. We don't have tape measures that are measured in light years, let alone the millions of light years that we need. We can't bounce radar signals off of them the way we can in the solar system to measure the distances to the planets. Instead, we have to use more indirect methods. One of the key tools that we use is a method called a standard candle method. And it works kind of the way it sounds. If you imagine a candle has some intrinsic luminosity to it. And if you observe that candle close by, it'll seem bright. And if it is farther away, then it will appear fainter. Candles, of course, are not bright enough to be seen across the Earth, let alone intergalactic space. So we need to use something that's a lot more intrinsically luminous. And the tool that we use in astronomy that seems to work the best is a type of explosion called a type 1a supernova. A type 1a supernova is the thermonuclear detonation of a white dwarf star, and it produces so much light that it is visible across most of the known universe, at least for a limited amount of time. However, you don't need to know the details of how these work in order to use them as a standard candle, any more than you need to know the details of how a candle actually works and how the wick is lit or how it stays lit to understand that a candle will look fainter if it's farther away. The key is that when we observe supernova explosions in galaxies, if we observe that the supernova is faint, then we know the galaxy is farther away. And if we observe that it is brighter, then we know the galaxy is closer. And we can get relatively good relative distances using this method. The other way we can estimate distances is by looking at things that are called standard rulers. This is illustrated here as well. If we had a ruler and we knew something was intrinsically a certain size, if we observe it and it's at a range of different distances, obviously it will look smaller if it's farther away. And we can use the angular size to tell us information about how far away it is. So all we need is something that is large enough that we can observe it across most of the known universe. That would be really nice. I'll come back to that. What I first want to get at is how we know that these galaxies are all moving away from us. And I was having dinner last night with my family, and I was trying to decide whether or not I needed to explain redshift in my presentation. And I said to my wife, I said, if I just simply said during my talk that galaxies are moving away from us, and that's why they are shifted to longer wavelengths, and that's why we call it redshift, do you think most people would know that? She just laughed at me. I'm sure that many of you have been coming to these talks and have heard people talk about redshift in the past, but I know not everyone has. And so I thought I would introduce the idea. The tool that we use in astronomy to measure velocities is spectroscopy. And we use something that is like the Doppler effect. In fact, exactly, it is the Doppler effect that you may be familiar with for sound waves. If a siren, for example, is moving towards you, it will appear higher pitched. It's shifted towards higher frequencies. If it is moving away, it's shifted towards lower frequencies. The same thing happens with light. It's just that the wavelengths of light are quite a bit closer together than sound waves. If a galaxy is speeding towards us, its light will be blue shifted. Its light will be shifted to have shorter wavelengths. And we can measure that with spectrographs. If something is moving away from us, then the light is shifted to longer wavelengths, larger wavelengths, and so it will appear redshifted, where we use the terms redshift and blue shift because when light is at longer wavelengths, that is also the part of the electromagnetic spectrum that we see with our eyes as red, and shorter wavelengths we perceive as blue. So that's the origin of this term. But the key points of this to remember for the rest of my presentation are that redshift is synonymous with moving away from us, and the larger the redshift, the faster something is moving away from us. And the amazing, amazing result, not a new one, but the amazing result is that when we measure galaxies in the universe, basically all of them are moving away from us. Furthermore, there is a very good correlation between how far away they are and how fast they are moving away from us. That is, and this told Edwin Hubble 100 years ago, that our universe is expanding. So why is that the case? Oh, first let me show you some of the observations. This is a measurement of galaxies in the nearby universe, or this is really representative of measurements of galaxies in the nearby universe. This is showing distance to galaxies on the y-axis and their redshift along the x-axis. And this is showing that galaxies that are farther away are ones that also have larger redshifts. So this is an idea. This is a measurement that was popularized by Edwin Hubble And he really convincingly showed this correlation existed, and that immediately told astronomers of the day that the universe was expanding. That was really fundamental because up until that time, everyone thought that the universe was static. It didn't make sense to people like Einstein that the universe was static because Einstein, better than anyone, knew about gravity, knew that galaxies should be attracted to each other. And so a static universe didn't make any sense. It thus was great when Hubble showed that the universe was not static, but then surprising that instead of contracting, the universe was actually expanding. So why is this evidence, though, of the expansion of the universe? Maybe I should cover that first. This is an illustration. As you can see, I like to make little illustrations with PowerPoint. And my artistic skills really shine through. I hope you like them. This is showing an example of how uniform expansion means that more distant objects will be moving away from us more quickly. Here's my very toy universe. I only have 5 galaxies in this universe because I got tired of doing copy-paste. But that's fine. I think 5 is enough. And here are these 5 galaxies at the beginning. And then sometime later, they're all spread out from one another a bit. A next time later, they're spread out even more. And at the bottom, they're spread out even more. So we're seeing that at each step, the distances between them are changing, and they're all changing uniformly. It's like they're on a sheet of, they're like little pricks on a sheet of rubber, and the rubber is being stretched out. The reason why this corresponds to more distant objects moving farther away or moving away from us faster is because if we imagine ourselves on any one of these galaxies and we look at the nearest objects, we see that they are moving away from us at a certain speed. But now when we look at the next galaxy over, we see that the distance to that next galaxy has increased by even more than the distance to the nearest galaxy. And because it's increasing by a larger amount, the velocity of it away from us must be larger. Furthermore, this is true regardless of which galaxy you imagine as your starting point. If you imagine that you're on this galaxy here, and you're looking at these 4 neighbors, you can see that as each time step passes, the most distant one has moved the farthest away. Its distance has increased by substantially more than the nearest one. So its velocity will naturally be larger. That is why this correlation that I showed you between distance and redshift means the universe is expanding. That is the reason why we interpret this as the uniform expansion of the universe. And this ultimately led to the idea of the Big Bang, the universe forming in some primordial explosion 14 billion years ago. And we're still seeing the expansion of that today. Astronomers have been really excited about studying the expansion of the universe because we know that there is matter in the universe. We only have to look around this room to see that there is matter in the universe. And we know about gravity. We should be able to predict very precisely how fast the universe is slowing down because of gravitational forces. If I had a tennis ball in my hand and I threw it up in the air, I would expect that tennis ball to gradually would move up fast initially, but it would start to slow down over time because the force of gravity is pulling it back towards the Earth. Similarly, the galaxies in the universe that are flung out in this primordial explosion, the matter that's flung out in this primordial explosion should be slowing down over time because the force of gravity is pulling on all the matter in the universe. So we were very excited in the late 1990s to finally be able to measure distances well enough out beyond the local universe to study the expansion history. what I've done just now in switching between this slide of the nearby universe, which only extends out to a redshift of 0.05, to this one, where I'm now extending out to a redshift of 0.8, is I've taken an enormous leap out into the distant universe, and in fact, extending billions upon billions of years into the past. And you can see that these data points are, they show clearly that the universe is continuing to follow a relationship between distance and redshift, but it's not immediately obvious from looking at this whether the expansion rate is speeding up or slowing down. Although if you think about it very closely, you might start to get a little puzzled, because you might say that these most distant objects actually they're farther away than the relationship that I've drawn on here. At least if I had remembered to tell you, I remembered to tell you that this relationship was the expected expansion history for a matter-dominated universe. But I'll make it easier, and I'll convert this into a format that I like to look at, which is, instead of looking at distance versus redshift, I'm going to look at the expansion rate versus redshift, because that's really what I'm looking for. I'm interested in seeing how the expansion rate is slowing down over time because of matter. And that's just the inverse of the slope of this relationship. And this is what happens if I convert this figure into the expansion rate history. I see this. Here's expansion rate on the y-axis, and now the same redshift or look-back time along the x-axis. And now I've remembered to label the solid line, which is what the expansion history should be if gravity is slowing down the cosmic expansion rate. We expect the expansion rate to get smaller with time because of gravity. If anything, you might see, well, the data are not consistent with that. And in fact, it looks like the data suggests the universe is accelerating. If I add some lines on here, it will become more clear. This is showing now what the universe would do if the expansion history was constant. That's something that's only going to happen if there was no matter in the universe. That's not true. And this is our current best estimate from cosmological models to what the expansion history of the universe actually is. And those unequivocally show that the universe's expansion is accelerating. This was a huge deal in the 1990s. It led to the people who led these teams won the Nobel Prize in Physics, because they showed that there was this additional component to the universe that no one had a good explanation for. It was also very impactful on me because it completely destroyed my naive view that I could take the 4 fundamental laws of physics and figure things out, because it showed that our knowledge was actually incomplete. You may look at this and say, oh, well, this doesn't look that convincing. I'm sure some of you are thinking that this doesn't seem super convincing. So what I want to do is I want to fast forward to show you the latest results on the accelerating expansion of the universe from the most recent survey of supernovae in the high redshift universe. That survey is called the Dark Energy Survey, and it was a project that I was somewhat involved with for many years. And over the course of that experiment, we measured distances and redshifts for about 1,500 supernovae, not a few tens, as were used in the original research back in the late 1990s. With those results, it looks quite a bit more convincing that a matter-dominated universe just doesn't work at all. This is now switching back to plotting the distance to supernovae versus their redshift. The dashed line here is showing the non-accelerating universe, So that's the universe if it had been slowing down because of gravity. And this, in contrast, the one that goes through all of these points that represent the supernovae, that is really clearly showing that the universe is actually accelerating. That's what this model is here. In this model, this is requiring something called dark energy, and that is the name that astronomers and physicists have come up with to explain whatever it is that's causing this accelerating expansion. But I want to emphasize that when we use a term like dark energy, or we use a term like cosmological constant, which I'll talk about in a moment, this is a word that describes a phenomenon. It is not the same as saying gravity, which we have a very well-developed theory for. So with this information, we set out, however, to make this measurement even better. Because, as I alluded to, what we have here is a really good measurement that the universe is accelerating. We have maybe even a great name for whatever's doing it, dark energy. But we don't have a physical understanding of what this dark energy is. And how are we going to figure that out? Really, the only course of action in science is to apply the scientific method. We need to collect data. We need to generate hypotheses for what could be going on. And then we test those hypotheses against the data. If the hypotheses work out, we collect additional data to test them further. And eventually, that turns into a scientific theory if the hypotheses or this theory ends up always matching the observations. So what we really need is we need a lot of measurements to explain what's going on. At the time that the accelerating expansion of the universe was discovered, it was pretty clear that it was consistent with this old idea that there might be some cosmological constant that's producing the expansion of the universe. But the physical ideas for what that actually meant were not a great match to the data. This is a picture, an artist's illustration of what the vacuum of space might look like on the sub microscopic scale. And there were lots of ideas that it could be that fluctuations in the vacuum of space could lead to some dark energy, some negative pressure associated with space-time itself that would cause the universe to expand and continue to expand. However, the best estimates for the size of this effect were unfortunately off by 120 orders of magnitude. That's a 1 followed by 120 zeros. I know from my experience in many math classes that if I turned in a math homework and I was off by that much, I should not expect full credit. Yeah. So it's a nice physical idea, but it is not something that is widely accepted as the correct answer. To tell you about how we're going to try to explore this further, I now need to share another physical idea with you, which is the concept called the equation of state. The equation of state is another term that we use to try to understand or explain the properties of dark energy. The equation of state, for those of you who have experienced chemistry class at some point, you may remember that there's a relationship between pressure and density. And for an ideal gas law, pressure and density are linearly related to one another. In this equation, I have pressure P is equal to some constant times the density rho, the Greek letter rho. For an ideal gas, W is equal to +1, and they're positively correlated. If you don't know anything about chemistry, but you have pumped up a bike tire at some point in your life, or have seen it happen, you know that if you put more air into the tire, the pressure will go up. that is the same as saying that there is a positive value of W in the equation of state. And that's how normal matter behaves. Unfortunately, for explaining cosmic acceleration, we need to have an equation of state that is negative. And in fact, the cosmological constant has W equal to -1. I can't really emphasize just how weird this is. There is nothing within our everyday experience that at all behaves like this. It makes no sense, and we wouldn't even be talking about it if the universe's expansion was not accelerating. So the goal of my research is to figure out what the value of W exactly is, and ideally provide good enough measurements of the expansion that we can use these measurements to test different theories for what the value should be, perhaps even how it changes with time, if it does. And that is why I and hundreds of my colleagues constructed the Dark Energy Spectroscopic Instrument at the Mayall Telescope on Kitt Peak. This is a project funded by the US Department of Energy, Office of Science, as well as with funding from many institutions around the world, all of whom contributed to the project in various ways and continue to contribute to the project in various ways. We're using this beautiful telescope that's inside of that dome, the 4-meter Mayall telescope. And with this telescope and a few hundred other scientists, you can build some really fabulous scientific equipment. This is a map of all of the instrumentation we built for DESI. It starts with light that bounces off of the primary mirror of the telescope, and it passes through 6 lenses that are each about 1 meter in diameter. That's a really big lens, a meter of glass that's precisely polished. Then that light comes to a focus that is only a few microns across, tens of microns across, and it goes into one of 5,000 fiber optics cables, each of which are positioned so that they can collect the light of individual objects that are our targets. They are positioned, centered on the light of those targets to only a few microns. That's a small fraction of the diameter of a human hair. The light from those objects then passes through about 50 meters of fiber optics cable and ends up in one of 10 spectrographs that we have in a special climate-controlled room. And that climate control helps to keep our data calibration very stable over the course of our survey. We here at Ohio State contributed a lot to the DESI project, including building many of the components of the spectrographs, as well as the instrument control system. And we continue to be very involved in the analysis of the data from this project. But I do emphasize that it's a collaborative effort that includes people across the US and around the world. While I will not talk a lot more about the details of the instrumentation, I do want to advertise briefly that we have a really nice planetarium show that was created. Actually, the main producer was a graduate student at Harvard named Claire Lamont. And it's a wonderful planetarium show that describes the history and construction of the DESI project. And we have shows available at the Arnie Sledebach Planetarium here on OSU's campus. What I'm going to show you with now is a quick view of what our data look like with just the first year of observations from DESI. The DESI project began collecting data in May of 2021. And in the first year, we collected measurements of about 6 million galaxies and quasars. Here you can see the structure of these galaxies distributed in space. It looks kind of like a cone or a triangle because we're looking up at the night sky and we see sample a smaller volume of space nearby, but progressively larger and larger volumes farther and farther away. You can see that there's a lot of structure in the universe. As we fly through it, we're looking at structures that range from within a few tens of millions of light years of the Earth to, as we go through the survey to greater and greater distances, we're looking at objects that emitted their light only within a few billion years of the Big Bang. And one of the things that's really remarkable about this is that we can use the distribution of galaxies to actually measure a standard ruler and measure distances. To illustrate this, I want to show another animation developed by some of my colleagues within DESI about a pattern in space called baryon acoustic oscillations, which is the standard ruler that we're looking for that is large enough to be seen across the known universe. It's a ruler that is about 500 million light years across. That's pretty big. The baryon acoustic scale is a slight overdensity in the distribution of galaxies at one specific separation that we can measure by looking at the clustering of galaxies in space, like that ruler was indicating. It's hard to measure, though, because the individual BAO scales are all overlapping with one another. So we need to do a very careful analysis of our data to pull out the signal. However, when we do that, we can get a really nice measurement of the expansion rate. And this is a measurement of the expansion rate from the latest results from DESI. These came out about a year ago in April of 2024. And these are showing our measurements of the expansion rate at a range of different distances with different parts of our sample. These individual cutouts are showing the quality of the measurements of this BAO scale over density. And they point to the redshifts at which they are measured. And from these, we really clearly see this expansion history of the universe. And for reference, that solid line is a cosmological constant with W equal to -1. The really fascinating thing, though, that came from our measurements is that we saw a little bit of evidence that the cosmic acceleration is not perfectly consistent with a cosmological constant. And this opened up the question of, does dark energy change with time? You may imagine that there's probably only one way something can be constant, but there are a lot of ways things can be not constant. And since we're not even really sure how dark energy could work, we're at the pretty early stages of trying to figure out what is even the best way to describe it not being a constant. One of the ways that we use in the scientific literature is talk about the current value of the cosmological equation of state, W, and how it might change with time. So we have two variables instead of one. We have a W naught, which is the current value, and WA, which is how it changes over time. There are lots of different theories that make predictions for what these two values should be. They have cool names, like we have thawing models, where W changes from -1 to a larger value of W that is closer to being a positive number. We have things like emergent dark energy, where W is decreasing to -1. And then my personal favorite is something called phantom crossing. This is an awesome name, and the implications of it are equally cool. Maybe. Well, I don't know if cool is the right word. But if W is less than -1, then that means that the dark energy component becomes more and more powerful for some reason as the universe continues to expand. And that would eventually lead to something that's called the Big Rip, which is where the universe expands so much that all of the other forces, gravity, electromagnetism, the strong and weak nuclear force, are all overwhelmed and all the matter in the universe gets shredded apart. That sounds bad. It sounds bad. Fortunately, I'll add on our best measurements of these parameters from the latest DESI results. And that's represented by these colored ellipses down here. We have a lot of uncertainties in our measurements that we have to carefully propagate through. And so instead of putting a single point on a graph like this, we instead represent our uncertainties with these ellipses. So there's two things about this that I want to get across to you. One is if you look at this, you say our best values seem to be where W, the current value of W, is a little bit larger than -1, and that its time dependence looks like it's a little bit negative. What you can also see from this is it's a little bit inconsistent with a cosmological constant, which is quite interesting. And the good news is that it doesn't seem to actually be less than -1. It's not crossing into this phantom regime. At best, you might say it's a phantom menace. So what does this mean for the four fundamental forces of nature? It gives us a way of now trying to figure out what is the missing component. So in addition to the four fundamental forces I learned about in college, we need to add something else. I'm not sure if we're ready to even call it a fifth force. Some people like to use the term quintessence because it's a fifth of something that's essential. But we don't really have a theory that we can quite test yet. However, with DESI observations, we're going to be collecting a lot more data. And in fact, we have collected a lot more data already. The results that I've shown you so far are just from our first year of observations. We've now been in operation for about 3.5 years. And in March of this year, we're going to announce our new results from the analysis that we're currently finishing up. So stay tuned for that. In the meantime, you might be wondering, what are the implications of all this? How does it affect our lives? Should we be concerned about the fate of the universe? And what are the practical implications? How does it affect our lives? Well, I think it's fascinating to think about the fundamental nature of the universe itself. And so it's a fun topic to think about. What could be causing cosmic acceleration? What could be overcoming gravity on the largest scales? That's interesting. Is it something where we should be concerned about the fate of the universe? I would say no. I'm not, personally. Even if we are in a big rip scenario that's many tens of billions of years in the future, there are much more immediate problems. Like, for example, the sun's only going to last for a few other billion years. That's, I'm sure, what everyone was thinking about. And then, another question that I get asked occasionally is, what are the practical implications of this? And I have no idea. I have no idea. This is truly basic research. However, I can draw some analogies, which are fun. When James Clerk Maxwell was writing down the equations of electricity and magnetism in 1865, I am pretty sure he would have not told you that understanding this was critical for producing consumer electronics. In 1916, when Einstein was developing the general theory of relativity, he was not thinking about corrections that needed to be applied to the global positioning system. So who knows? But with more observations combined with the smart theorists who are thinking about ideas that we can test with these data, we might just figure out what that additional component is. So to summarize, what I hope I've shared with you today is that we've been conducting the largest spectroscopic survey of the night sky that's ever been obtained. We've mapped now over 20 million galaxies and quasars. We've easily surpassed all previous spectroscopic surveys of the universe that were ever obtained before we started. And our results are providing this tantalizing evidence that dark energy might not be a cosmological constant. And therefore, it gives us an opportunity, a better opportunity to actually figure out what it is at a very fundamental level. So I encourage you all to stay tuned for our next press release and data release, which will be coming out in just March of this year, where I hope we'll have some more exciting results to share. In the meantime, thank you very much for your attention, and I'm very happy to take questions.
Okay, so we'll take some questions for Paul, and just so you know what's going to happen, we'll do this for like about 10, 15 minutes, then we'll all go upstairs to the traditions room for a reception. There's coffee, there's cookies, we can talk, and have a chance to meet the speaker and all of that. But let's start with the questions, and in the Science Sunday tradition, I like to call on students first, if I see any. The younger they are, the better their chances of getting called on first. There we go. Go ahead, just yell it out, and he'll repeat it.
Where I can see those results coming out this month.
Okay, so the question is where can I see these results in March? We are planning a press release associated with what's called the Meeting of the American Physical Society, and that will be on March 19th, to be precise. We will be having press releases. They will be press releases from Ohio State, as well as from the Lawrence Berkeley National Laboratory. We also plan to spread them on social media sites. And so there should be a lot of ways to hear about them.
Okay, somebody else? Let's see. Any of you guys feeling brave? Not today. Okay, go ahead.
Based on this plot, obviously the cosmological constant's not a constant, but like over, say, 1 billion years or 10 billion years, how many orders of magnitude does it change?
Yeah, great question. So the question is, it doesn't look like this is consistent with a cosmological constant, but how does it change over time? How does the value of W change over time? Yeah, and so first I need to say that our best values from fitting the data suggest that it's not a cosmological constant, but we are not prepared to rule it out completely. That may sound a little bit of a wishy-washy statement, but the analysis that we do is pretty complicated, and we have to combine data sets from multiple experiments and understand the details of how each of those experiments work as well, what assumptions other experiments made when we combine them with our own measurements. And so these results are formally inconsistent with a cosmological constant at what scientists would call a 3 to 4 sigma level, which is ruling it out with high significance. But in practice, because there are other uncertainties that we may not have taken into account, it would not be, it's not out of the realm of possibility that a cosmological constant is not correct. So that's just that's the full disclosure. If this was a commercial, this would be all the things that I would say really fast at the end that you wouldn't be able to read or hear, but are in there for legal reasons. And so that was my legal disclaimer. That being said, these are numbers in a linear equation that we can use to predict what the value of W was at any previous time. And it's changing by pretty small amounts, like a couple tenths.
Okay, go front row, go ahead.
Yeah. I really like your talk. Thank you very much. Can you please help me understand this graph a little bit more? Because the way I'm reading it is that in the past, your predictions say that the cosmological constant was somewhere between -0.5 and -1. So if you extrapolate this into the future, it should increase. Well, it should decrease, right? Further. Mm-hmm. Wouldn't that mean the big rip?
Okay. Yeah, great question. Yeah, so I didn't actually put the equation that combines W naught and WA onto my slide. Perhaps I should have. The equation, however, takes a current value of W naught, and then it adds on WA times an expression for the past values. And so with these values, there is some possibility that in the past, at higher redshift, the value of W from solving this equation was more negative than -1, which might be what you're picking up on, which is very good. However, it has moved to being less than -1. And it being less than -1, sorry, greater than -1 in the future is moving us away from the big rip scenario.
So the future is on the y-axis. The future is this way.
It's not really the future. This is how it depends upon time. This is not the future value of it. Yeah. Yep.
Let's see, hat guy, go ahead.
What's the difference between dark matter and dark energy?
Yep. Great question. So what is the difference between dark matter and dark energy? And the difference between the similarity between them, other than they're both called dark, is that dark matter we also don't understand. It's kind of embarrassing, actually, to give these talks and say, we have this great model of the universe. It fits our data really well. The only problems are we don't understand what 90% of it is made of. So dark matter is a form of matter that only interacts gravitationally with other matter, including with itself. Normal matter, like what we are made out of, interacts with matter, but it also interacts with electricity and magnetism, or energy. We can absorb light from the sun. We see that normal matter that creates like photovoltaic cells for solar panels, that can turn sunlight into electricity. Dark matter doesn't do any of that. All it does is it gravitationally interacts. Dark energy, in contrast, is some property of space-time. Well, I shouldn't even say that. It could be some property of space-time that is causing this acceleration.
Okay, sir, go ahead.
A lot of this is focused on how it's changing in the future. Have you tested this against what has happened in the past?
Yes. So the question is, this is very much looking at an equation, which is really the seeds of an equation that would describe how dark energy, the dark energy equation of state, in fact, changes over time. And actually, what we do when we analyze our data is we measure these quantities for what has happened in the past. So these values are only a good fit to our data based upon the past history. And so they work really well with our observations of the distant universe. And then what happens in the future is just an extrapolation of these forward in time. And that might work, but we don't know.
Questions over here. Go ahead, sir.
Yes.
Just yell it out.
Okay, so one of your original statements, if I remember correctly, was that all galaxies are expanding away from us.
Yes.
Does that imply we're near the center of the original point of?
Yeah, that's a great question. So I said early on that the universe is expanding and that we observe that all galaxies are moving away from us. The more distant ones are moving away fastest. You might wonder, have we done anything? Have we done anything wrong? And the answer is no. And this is a very challenging concept to conceptualize, but a way I like to think about it is, imagine that all of the galaxies in the universe, let's imagine that the universe is just the surface of a balloon, and all of the galaxies are painted onto the surface of the balloon, and that balloon is getting blown up by adding air to it. All of the galaxies are going to move away from all the other galaxies. And there's no one special place that is the center of the surface of that balloon. Instead, the center, if there was a center, is when the balloon was collapsed down into a single point before we started to blow it up. So that point, the center, is in another dimension, which is the dimension of time, and that's the origin of the universe itself.
Let's see, I want to try to, any students out there? Oh, there we go. Go ahead.
When we look further away in space, we see further into the past. why is it that we can't like see the Big Bang itself?
Yeah, that's a great question. So the question was that when we look into the past, we see farther, or when we look at farther and farther distances, we see further and further into the past. Why can't we see the Big Bang itself? The closest we're able to see to the Big Bang is about 375,000 years after the Big Bang. And that is the region of the sky that emits something that's called the cosmic microwave background. Before that point in time, the universe was so dense and so hot that it was just a plasma that existed in the universe, and we could no more look deep into that plasma than we can look into the layers of the sun. And so that's why it's hard to look closer to the Big Bang than about 375,000 years after it.
Okay, let's take one more question. Oh, there we go. Miss.
So, like, with the pictures, are they actually all those colors? Because when I look at the night sky, I only see one colored stars. Like, I don't see all the really colorful stuff.
Yeah, so that's a great question. When I was showing you pictures at the beginning, oops, I was going to advertise that. We can come back to that. Well, I won't be able to find that quickly, but you all remember I showed you this beautiful picture at the beginning of the Hubble Ultra Deep Field. It had galaxies that were a wide range of colors. And I think we all experience when we go out and we look at the night sky that it kind of all just looks black and white. And why is that? The basic reason is that it's our eyes. When we are adapted for night sky conditions, our eyes' response is shifted towards bluer light, and it's a lot harder to distinguish colors. And so those colors are there. If we had infinitely bright galaxies in the sky, we would be able to see those colors as clearly as the colors on this image. It's just that it's hard to see with the unaided eye. If you look through a telescope at something like a nebula or even a galaxy, if the telescope is big enough, you will start to be able to see the colors. But you need to have a lot of photons. You need to have a lot of light in order to make out the colors.
But in the DESI movie thing that you showed with the flying through, those colors were just put on by hand, right?
Yes. Oh, yes. Sorry. Yes.
This one.
This one. Yes. The individual objects in this image are just points that represent where galaxies are in space.
Okay, so that seems like a good spot to stop. So what, like I said, what we'll do is can you go to that advertisement slide?
Yeah.
We're gonna go upstairs to the traditions room, and you get a chance to meet the speaker and ask more questions. And then, by the way, we have another public lecture coming up. So many of you are on the Science Sundays email list, and if you are, you'll soon get an email about this. This is a different lecture we're doing. This one we're doing through the Center for Cosmology and Astroparticle Physics. Sean Carroll is a noted scientist and science communicator, and he'll be here on Feb 19, not here in this room, but in Mershon Auditorium. And so if you're not on the Science Sundays email list, you could fix that. And we send about one email a month, so it ain't gonna kill you. So with no further ado, let's thank our speaker, Professor Paul Martini.
Thank you very much. Thank you.